So let's start. And let's start by recalling what we learned last time. So what we learned, can you please stop talking now? So we learned that with a system of linear equations, we can associate a matrix. So all you do is you collect the coefficients of your variables. So that would, and you arrange them in a matrix form. That would be the matrix of coefficients. Augmented means that you just augment this matrix with the constants which come on the other side of the equations. So with that, you have an augmented matrix. So these two kinds of matrices are associated with your equations. And how do you do it? Each row in the augmented matrix represents one equation, and each column is fixed by collecting the coefficients of one single variable. So if you are looking at one column of your matrix, that means you're looking at the coefficients of one particular variable. So for example, if I look at this system, here you have three variables A, B, and C, and you have three equations given to you. So it's a square system. Whenever you have, this is a 3 by 3 system. Whenever you have n equations and n variables, you call it a square system. And these are the systems which we are looking at for now. So with this example system, you can associate this matrix. So what you're doing, collecting the coefficients of variable A in the first column. So this is the column of A's. This is the columns of B. You have a 0 here because in the second equation, you don't have a B. Or in other words, the coefficient of B is 0. This is the coefficient, this is the column of C's. And this column, which comes after this line, are your constants. And each line over here, so this is the first equation, this is the second, and this is the third. So you have just cleaned up the extra symbols of plus, A, B, C, equality, and written it out in a more clean way, because you know what you are talking about, so you don't have to write all of those things again and again. That's the whole idea for now. Now, if I restrict to just the coefficients of variables, like this part, this is called the matrix of coefficients. And if I consider the whole thing, including the constants, that becomes the augmented matrix. We will be mostly dealing with the augmented matrix. Now you can take this matrix and transform it. So the matrix associated with this system can be changed and it will still describe the same system. So it's the same idea with the equations. You can change the equations by doing some allowed operations and it still describes the same variables, same system. So from the allowed operations on your equations, you can translate those into allowed operations on the matrices, on this matrix, associated matrix. So what were those allowed operations? Interchange of rows, because that corresponds to just renumbering the equations. Writing, if I just exchange these two equations, write this one first and this one later, that will correspond to writing this row first and the first row, replacing first row with the second row. That obviously cannot change anything. You just collected your equations in a different ordering. So it still describes the same system. Then just like you can multiply an equation by a number, an equation becomes a row in your matrix, so you can multiply a row by a number. And similarly, like you can multiply an equation by a number and add to another row. That thing becomes simply, because row is a equation, becomes multiply a row by a number and add to another row. So these three allowed things you're always allowed to do, and your matrix, the new matrix you get, is still describing the same system. And these are called the elementary row operations. Why would you do these operations? Because you have a goal in your mind, you want to solve the system. In terms of the matrix, you want to bring the coefficient matrix, this part, into a strictly triangular form. Because once you have that, then you have a, for a square system, you have a, we know that we have a solution. And it's actually a unique solution, because then we can do back substitution to get the complete solution. So this is what we did last time. Any question from here? So now let's move to what we're going to do today. So we're going to ask a few questions. So main question is, will this process always work? That is, will we be able to bring any square system? So right now I'm asking the questions about square system to a strictly triangular form. Because I know that if I have a triangular form, I have a unique solution. But can I do it always? Does it always work? My theorem only went one way, that if you can bring your matrix to a triangular form, strictly triangular form, then you have a unique solution. But I don't know if I can do that. So that's what we're going to look at. And if the answer is in negative, which we will see that it indeed is negative, then what can we do? What strategies we have to find the solution in that case? And then what if the system is not square, or number of variables is different from number of equations? What strategies we have and what general statements we can make in that case? So as always, let's start with an example. Now, because we are a little bit familiar with associating a matrix with equations, so I'm not even going to bother to write the system of equations. I just give you the matrix and augmented matrix, and you know that you are given a system of linear equations and you know what those equations are. So first of all, here, since in the coefficient part, you have 5 columns. So that means you have 5 variables. And since you have 5 rows in this matrix, that means you have 5 equations. These variables are just some unknown. You can give them any name you like, x, y, z, w, u, or x1, x2, x3, so on. We have 5, so I can just label them from x1 to x5. And now I'm going to try to bring it to a strictly triangular form. So this is the strategy. You always do this. You start from the first line and look at the first entry in the first row. You want it to be triangular, so this better be non-zero. If there's a zero over here, then you know what you need to do. You need to exchange rows to bring a non-zero entry over here. So over in this case, we already have a non-zero entry, so we are fine. So we start with this guy. And the goal is to make everything below it zero, because that's what a triangular matrix is. Let me just tell you. Triangular means you're going along this diagonal and you're going to make everything below this diagonal to be zero by adding rows. Now, the first thing to do is to make this zero. How can you do that? Well, if I just add this to this, the first entry is going to be zero. Just multiply by 1. I'm not even going to write add, because I'm always adding the rows. I'm just going to write the number with which I'm multiplying this my specific row. So over here, this is just terminology. The terminology they create just to confuse people, just sound more academic, but they just mean simple things. So pivot is just the element which you are adding to other elements. So multiply this row by 1 and add over here. So I'm going to start changing it. You get a 0. Here, maybe let me change the color. You get a 0 here. When I add these two, what do I get? Again, a 0. Add these two, I get a 1. Again, a 1 here. And when I add these two, I get a 2.
Sir, why will that be 0? 1 नहीं होगा, 1 into 1 plus 0.
यहाँ पे क्या था? That's why I've written. So 1 plus 0 is 1, right? And when I add this to over here, I get, again I get, it was -1, so I get a 0. So I'm going to do the same thing with this row. I want to bring a 0 over here. So I take this, multiply by 2, and add to this row. So I'm going to get a 0 here.
Sir, I have a question.
Yeah.
So aren't we going to swap equations 1 and 2 because हमने ऊपर में भी तो 0 रखना है ना first उसमें अपने.
पहले हमने 0 नहीं रखना. पहले हमने we have to keep the first one non-zero.
Okay, sorry. Got it.
Because we want a strictly triangular. So on the diagonal, our best effort, we're going to do our best effort to keep non-zeros on the diagonal.
Got it.
So I got a 0 here, multiply by 2 and add to it, this was a -2. Again, I get a 0. And multiply by 2, add to this one, you get a 2. And over here, I get a 2 again. And 2 plus 1, I get a 3. And again, 2 plus 1, 3. I think I'm not going to complete. I'm just going to do this first step just to show that I'm going to bring zeros over here, then I'm just going to tell you the answer. Now this row, the fourth row, I don't need to do anything to it because below, this is my pivot. Right now, all I'm doing is bringing everything below it to be 0. And this guy is already 0, so I don't need to do anything. But if in the fifth row, I need to make it 0. And this time, I multiply by -1 the first row and add to it. So I get 0, again a 0, and -1 plus 2 gives me a 1. That's why if I had a nicer pen, I could just press it and erase it. This is just taking way too much time. So again, -1 plus 2, 1. And -1 plus 4 gives me a 3. And over here, I get -1 plus 4, again a 3. So this is after my first transformations, taking the pivot from the first row. And I have succeeded what I wanted to do to the first column. Now I'm going to move to the second column and do the same. So you don't do anything to your first row. In the second step, you pick up your second row, and what you're going to do is change the row third, fourth, and fifth, and not do anything to the second row. But I have a problem over here. The problem is that I want my pivot. Pivot is always non-zero. Because if the pivot is 0, you keep multiplying it and adding it to other numbers, they're not going to change. So it's useless. And also, my goal is to get to a strictly triangular system. So for a strictly triangular system, on the diagonal, I want some non-zero element. Over here, it's not 0. What can I do? If I swap these two, it doesn't help because everything below it is 0. I can't swap it with the first one because what it's gonna do is gonna destroy my first line, my first row. It will bring a 0 up there. So I'm in a bind. I can't do it. There's a complete failure. I can do nothing. If I add this row, because I know that I have created zeros here, and if they are all zeros over here as well, if I want to bring over here 1 here, I may think like maybe I can add this row back here. It will bring a 1 here, but also a 1 over there, which I don't want. So I'm stuck. So that means you cannot always bring a system to strictly triangular form. So let me write it over here. Can't always bring a system to strictly triangular form. So that's done deal. Anyone has an objection if they have an idea what to do to bring it to strictly triangular form? You can think there is no way you can do it.
आप अगर शुरू में स्वैप इन कर लेते तो नहीं हो सकता था?
किसको स्वैप कर लें?
अगर हम शुरू में ही स्वैप इन कर लेते
नहीं, शुरू में स्वैप इन करने से किसको स्वैप करते हैं?
सर
जिसको भी मैं स्वैप करता, हुआ क्या है कि रोज ऐड करने से यहाँ पे सारे 0 बन गए हैं, लेकिन जैसे यहाँ 0 बने हैं वो यहाँ पे भी 0 बने हैं क्योंकि they are kind of same. This row, this column is kind of same as this, not kind of, exactly same. So problem ये आ रही है कि when I make the first column 0, the second becomes 0 as well. चाहे जिस मर्जी को स्वैप कर लूं, जिस मर्जी को पिवट बना लूं, इट वोंट मैटर। किसी भी से मैं स्टार्ट कर लूं, इससे स्टार्ट कर लूं, जब इनको जीरो करूंगा, इसको जीरो करूंगा तो ये भी जीरो हो जाएगा, इसको जीरो करूंगा ये भी जीरो हो जाएगा। So can do it. But should we go home? No, we keep trying. Because our goal is not, it's not like we are in love with triangular matrices. All we want is a solution. So we continue with the logic of eliminating variables. This variable, this first variable is eliminated in these equations. The second is also eliminated. But I say, let's keep going. Let's now try to eliminate the third variable. So I pick this one as a pivot. I move to the next column and pick this as a pivot. And then try to make all the entries below this one as zero. तो उसके लिए आपको क्या करना पड़ेगा? I'm not gonna do the whole thing, but I'm just gonna write what you need to do. -2 से multiply करके इसमें ऐड कर दें, you will get a zero here. -1 से multiply करके इसको इसमें ऐड कर दें, you will get a zero here. Similarly, -1 से multiply करके fifth में भी ऐड कर दें, you will get zeros below it. But you can see that you will also get all zeros over here in the fourth column as well. So again, you were expecting a pivot here, you won't get it. You will have to move to the next column, this one, because all these guys have become zero. So you move to this one and then start eliminating things below it. So finally, you get, so when I do this, the first step, I get zeros here. यहाँ पे क्या नंबर आता है? Let's just do it. 2 को -2 से मल्टीप्लाई किया था, -4 + 3. -1 just takes too much time to move the cursor. -4 + 3 -1. Please keep checking my calculations. I'll definitely make a mistake. नहीं -2 नहीं, इस रो में मैंने ये नहीं किया था. यहाँ पे अभी लिखा हुआ था 3, right? और 4. 3 था यहाँ. 3 था ना? So I have done on this row. I have done -1 × 2, -2 + 3, which is a 1. -1 से मल्टीप्लाई करो ना, -2 + 3, which is a 1. और आखिरी में मैंने क्या किया? Again, -2, -1, -2 + 3, so this gives me a 1.
सर आपने लास्ट वाली इक्वेशन को किससे मल्टीप्लाई करा है?
हाँ, दोबारा बोले?
सर आपने थर्ड वाली में जो पिवट बनाया है उससे क्या कहते हैं, और सेकंड वाली के अंदर जो एडिशन किए वो कौन से नंबर से मल्टीप्लाई करके किया?
ये यहाँ पे -2 से मल्टीप्लाई करके इसमें इस रो में किया है. -1 से मल्टीप्लाई करके 4th रो में किया और -1 से मल्टीप्लाई करके मैंने कौन सा पिवट लिया था? नाउ द होल थिंग इज मेस्ड अप एंड सिंस वी हैव
सर आपने पिवट लिया ये वाला, ये जो -1 आया है ना, ये जो -1 है जी।
नहीं, ये पिवट नहीं ले रहा था अभी, मैं इसमें नहीं था. So let me just write the answer because this is all now. We haven't kept track of the previous answers. वो हमने सब रब कर दिए. So let me just tell you कि फाइनली क्या आएगा. मैं पिवट यहाँ पे लूंगा और मेरे पास ये आंसर आएगा. अगेन यहाँ पे मेरे पास मैंने ये पिवट लिया था, ये दोनों कॉलम सेम थे, ये कॉलम भी सेम था. तो इस पिवट को लेके मैंने जब ये वाले जीरो किए इन द थर्ड कॉलम, द गाइज इन द फोर्थ कॉलम आल्सो गॉट जीरो. सो आई वाज लेफ्ट विद सम नंबर ओवर हियर. उस नंबर को लेके मैंने जब यहाँ पे जीरो किए इसके नीचे, दिस कॉलम वाज सेम, these two numbers were same, so they also turned out to be zero. Yes.
Shouldn't the third column, fifth row be -1?
Third column, fifth row.
It's going to be -4 plus.
नहीं, the fifth में मैंने -4 से नहीं किया, -1 से किया. तो तब तो मैं सिर्फ इसको देख रहा हूँ ना, this one. Well, let's not worry about the algebra because we will just lose time. So let's check the algebra later. Let's just concentrate on the concept. So we demonstrated over here that you may be stuck up with two simultaneous zero columns. Then you have to move to the next column, and use that as a pivot. Use that to eliminate things below it. So it's just that you are now trying to eliminate the rest which you get. So if you do that, you get zeros over here, left with this one, and when you eliminate things below this, this is what you get. In this case, now this matrix is not triangular at all. Well, it's triangular, but not strictly triangular. It's triangular because things below this diagonal are zero. It's not strictly triangular. So, because you have zeros all over here, on the diagonals you have zeros. So, it's not a strictly triangular system. But it has some other kind of form. Let me use this. It's like a dropping stairs. If I just pass through zeros, keep the zeros below this line, it's like a staircase which is going down from left to right. And so let's just call it staircase, but still, since we want to be fancy studying maths, so we call it something like echelon. Echelon just means staircase. And it follows our main strategy. Our strategy is that we are going to eliminate the variables one by one. And this is the best we can do in this case. In this equation, you have more variables. The equation below this, you have less. The equation below this, you have even less. And equation below that, you have even lesser. So that's all you are trying to do. One by one, try to eliminate variables. So if it's a staircase which goes down from left to right, that means you are getting lesser and lesser variables in your equation. And that should still do the job for you. So let's see that what equations we get out of it. So if I look at the row 4 and 5, what is the equation saying? Well, I have all these coefficients, x1, x2, all the coefficients are 0. So all this equation is saying 0 is equal to 0. So there's no information content. If you have a 0 row in this matrix, there's no information coming from at least that row. So that is useless. Similarly, equation 4 is useless. But let's write the rest of them. So I have x5 is equal to 3. Then I have 2x3 and 1x3 plus x4 plus 2x5 is equal to 0. x4 plus 2x5 is equal to 0. Just collecting the coefficients. And the first one is very simple. You add all of these guys. x3 is 0. And no, it's 1. Now, what can I do with these equations to solve them? I know that what's the solution of a triangular system, strictly triangular system. If I look at these guys, x1, x3, somehow if I could neglect, if I just collect the leading variables over here, x1, x3, x5, in these 3 variables, this system will look triangular. But what do I do with the other guys which are hanging around? So I keep these leading variables. What are the leading variables? The first non-zero variable in each row. So in this one it's x1, in this one is x3, and in this one is x5. So if I keep the leading variables on the left hand side, the system looks triangular. So take the other variables to the other side. x3 is a lead variable, so keep it here. Now if you think of x2 and x4, you have no information about x2 and x4. I can give a number to x2 and x4, any number. Let's say I assign x2 as, if I could, and x4 as -7. I'll generate some numbers over here. This will be 7. This would be +7, -5. This would be 2 or 3. 7 -5, yeah, 3. So I will have a system. On the right hand side, I have just numbers, and on the left hand side, I have a strictly triangular system in the lead variables, x1, x3, and x5. That means if I assign any value to x2 and x4, I'll have a unique solution. I will have one solution for all variables. Now I have a solution for all variables for each choice of x2 and x4. And I can choose whatever I want because I'm looking for all solutions. x2, there's no one is stopping me to give x2 and x4 any value. So I can as well choose these. Or I can choose some other. Anything you like. So what's happening that in this staircase, these guys which are lying on the same level, you keep them free. They become free. You can give them any value. But when you have a drop, that variable is fixed. So you keep this free, and then you have a drop, you write. So if you collect these dropping variables, which I'm calling the lead variables, you get a triangular system. And since you can give any value to x2 and x4, there's just not enough information in the system. Any value of x2 and x4 will do. You get an infinite number of solutions for this system. So our strategy becomes keep eliminating variables. Try to make it a triangular system. If it doesn't, if you encounter kind of a staircase, if you encounter a zero column and you can't do anything about it, just move to the next column and take the first non-zero entry in the next column and make everything below it zero and keep going. So you may end up with this kind of a echelon matrix, but this is also good enough. This also gives you solutions. Any question? Yeah. What do you mean substitution? Yeah, that's what we're going to do. We're going to do it afterwards. I just said that we have got the triangular system, this one. Now you think of these x2 and x4 as free variables. They can take any value. So how you find a particular solution? You give them a value and then you start back substituting. That part we still have to do. Back substitution we still have to do. All I'm saying is that you have got a triangular system. So now you can use your previous method of back substitution. Now you know that the solution exists through back substitution. Any other question? So let's take another example. The coefficients are same, I just changed some constants on the other side. Now you will do exactly the same things, and actually since these coefficients are same, you're gonna get exactly the same matrix from the left, on the left side of this dotted line. All that can change are these numbers, because I just changed these three numbers. So if you do the work, this is what you get. This is again the same thing as it should have been, because I didn't change anything on this side. You get an echelon. But these numbers got changed. So let's see what these equations are saying now. So what's the equation number 4? It says 0 dot x1 plus 0 dot 0 times x2, 0 times x3 plus 0 times x5 is equal to minus 4, or 0 is equal to minus 4. Similarly, equation 5 is saying 0 is equal to minus 3. What would that mean? Can 0 be minus 4? Huh? Yeah, that means that the information which was given to us in the equations was inconsistent. It didn't make any sense. So you cannot find 5 variables which satisfy these equations. That leads to absurdities. There are no 5 variables which have these relations between them. So this means that you have inconsistency. Inconsistency also means, so you can say it in two ways, that these relations are inconsistent. You can say it also as these relations have no solution because they are inconsistent. Yeah, I will. I uploaded the previous one. Didn't you get an email? I always send a notice as well. So now we have seen these three different possibilities. That sometimes we are just considering square systems. Sometimes you find unique solution, and we know when do we find unique solution? If our matrix can be reduced to a triangular, strictly triangular form. Sometimes you find infinite number of solutions, and sometimes you find no solution at all. So can we make a general statement about these three possibilities? That when will one happen and when will the other happen? The answer is yes. And to do that, we have to look at this staircase which we got. Let's look at it in a more careful way. How do we even define this staircase? You already, in a sense, have got the idea that what's the main idea behind the staircase. You want to make things below the leading numbers to be zero. So in any case, this is the definition. A matrix, now it doesn't have to be square. Like I could talk about the augmented matrix as well, or any other matrix. Square or not, is in row echelon form. So the staircase form is given a fancy name, row echelon, if it fulfills all three of the following properties. What are the properties? Pick any row. It could start with 0, that's fine. But after the zeros, the first number you encounter must be 1. This is kind of a, let me put it, more of an overkill. But that's how people call it, so we will stick with it. You will see why it's an overkill. But that's how you define it, that the first non-zero entry you encounter is 1. And there can be rows which are completely zeros, that's also fine. But all completely zero rows should come after the rows which have any non-zero entry. So like over here, this is in echelon form. If I don't take this guy, just consider the matrix on the left hand side of the dotted line, then this row is 0, this row is 0, but they come after the rows which have non-zero entries. So any row which is completely 0 should come after non-zero rows. And the second property, which is the most important one, is that for a non-zero row, the number of zeros in any row before the first non-zero number, so you have a leading number, you have leading zeros. So for example, in a row, you can have like 0, 0, 0, and then 1. So you started with 3 zeros. So any row below it should have more zeros to start with than this row. So leading zeros in row k plus 1 are more than number of leading zeros in row k. So let's look at some examples. The first one, is this in row echelon form? Each row starts with 1. So first property is yes. This guy has one leading zero, and this guy has no leading zero. The row below it has one leading zero, and the row below that has two leading zeros. So all three properties are fulfilled because it has no completely zero rows. So this is row echelon. What about this guy? Well, the other two properties are fine. This second row has more zeros than first, and third has more leading zeros than the second, but the first elements after zeros are not 1. So this is not row echelon because you have a completely zero row and it's above a non-zero row. मैं अभी स्वैप की बात नहीं कर रहा, अभी मैं सिर्फ मैट्रिक्स जो नजर आ रहा है वो देख के कैसा है. Any matrix you take, we're going to discuss it. Any matrix you take, if it's not in row echelon form, you can do the elementary operations and bring it to an echelon form. So right now we are just saying, is it right now in echelon form or not? So let's look at this blue matrix. Is this in echelon form? Why not? So someone said no, it's a good instruction to ask their opinion. Why it's not? Huh? Last row is completely zero, is below every non-zero row, so that's fine. आपने कुछ कहा था? So that's fine. The zero row is below all the non-zero rows. और क्या इसमें प्रॉब्लम है? इसमें क्या प्रॉब्लम है सेकंड रो में? Can one person speak at a time? I can't hear you at all. Huh? Why? That wasn't the property of echelon form. Echelon form, all it said that if you have some leading zeros, then the zeros in the row below it should be more than that. In the first row, there are no leading zeros. In the second row, there are 2. That's okay. Huh? Third row to completely zero row. That's fine. Completely zero rows ho sakti hain, as long as they are below. So it is in echelon form.
I'm sorry, sir. Second वाला क्यों नहीं है?
Second वाला इसलिए उसमें से वही जो मैंने कहा था ना overkill. वो overkill ने इसको kill कर दिया कि इसके वैसे तो ठीक है, but the leading numbers, the numbers after the leading zeros, they are not 1.
Oh, okay, got it.
Sir, तो strictly triangular form और इसमें फर्क क्या है फिर? Strictly triangular form 1 or 2 लग रही है मुझे.
Is a row echelon matrix, but not all strictly triangular are row echelon. So like this guy is strictly triangular, but it is row echelon. This guy is strictly triangular, but it is not row echelon. This guy is row echelon, but it is not strictly triangular.
So we can have a strictly triangular and this one as well. We can have both. Okay.
Now, this black matrix, is this row echelon? It is. Well, you can very much draw a line above the zeros. If it takes the form of a falling down stair, then, so like this guy, I don't know, it's like a step, it's not an echelon. This guy is a rising stair. We don't want that. And you have to take care of the ones, that the first thing is 1. So this is also echelon. This is not. Say again? Oh, the definition. I upload all these notes. If you miss something, not a big deal. And I uploaded the recordings as well, the videos. Now, by using elementary row operations, we can bring any matrix to the row echelon form. I'm going to show you right now how you can do it. But why would you want to do that? Because if you think about it, this row echelon form, why it's useful, why we make a big deal about it? Because the row echelon form of augmented matrix, it gives you the solution. It captures the essence of our elimination logic, that in the equations below, you have less and less variable. So finally, you will see a variable which is equal to a number. And then you will start back substituting. And when you will back substitute, you will complete the solution. If it happens to have a proper echelon structure, like you go 2 steps or 3 steps, then you fall down, then you will, the only difference would be you will encounter some free variables. So the variable which doesn't drop immediately, it becomes free, or it can be taken to be free. But as long as you have echelon form, you have a solution staring at you. But you can also have inconsistency, and we will shortly see when does that happen. You can also see that in the echelon form, if it's inconsistent or not. But first of all, let's see how can we make it, how does it give you a solution? So this one, if I'm considering a 3 by 3 system, this cannot be the augmented matrix, because 3 by 3 system, this is just the coefficient matrix because it's 3 by 3. So suppose I change it a little bit. It's low echelon form. It's still in row echelon form. So since it's in row echelon form, I have a solution that x3 is 2 and then back substitute. Let me change this as well. Now this one, the first one, is CM was strictly triangular. So we know that we will have a unique solution. This is not strictly triangular, but still row echelon. So it gives me x3, which is a lead variable, to be 3, and then another equation. So I take this to be free, x2 to be free, take it to the other side, and start giving it values. Take any value for it and you back substitute. You have a solution, because this whole thing is in row echelon form. Now this one, let me change this.
Sir, I have a confusion.
Yeah.
Sir, in the matrix 2, we can find the value of x3. Yeah, we can find the value of x3 is 3. But how can we find the value of x1 and the x2, because both are known and the
You cannot find the value of x2. x2 is free. You give any value to x2, you will have a solution. So this one, let me change it to like this: 2, 5, 3. It's actually strictly triangular, so you know that a unique solution exists. But still, we call it, it's not row echelon. He called it not row echelon, although it had the form of a falling stair. Just because some guy, probably Gauss, they did this overkill. They said that we should have ones over here. What's the advantage of having one over there? The only advantage is that you have already done one division, which you will have to do when you complete the solution. So the last one is equation is this: 7x3 is 3. So if I divide by 7, I will have this. And then this will become, and since it's an allowed operation, I can change this 7 to 1. Similarly, I can change this 3 to 1. And then I can change this 2 to 1 by dividing by 2, and this by dividing this by 3. So the only advantage is that if you insist on keeping it in row echelon form, is that when you back substitute, you won't have to do another division. You have done the division before. So the last variable has the solution staring at you. You just put it back and you have the solution for the next variable. Then you put it back, you have the solution for the next variable. It's just for, let's say, some algorithm you want to stick to. So property 1 is just an extra convenience.
Sir, so जो पहले वाला जो था, that's perfectly triangular but non-echelon.
Yeah. This one. Now this one, which is echelon, and I change it over here to get some solutions. Now let me this time change it a little differently. I have to add some constants. I add these constants. It's still echelon. But what is the last equation saying? The last equation is saying 0 is equal to 1. So it's inconsistent. Now I made it inconsistent. Now you know that what's going to happen. Whenever you are given the augmented matrix, you're going to try to make it echelon. And when you make it echelon, because all these zeros, maximum number of zeros come below, if you have a completely zero row in the coefficient matrix, and on the other side you have a non-zero number, then you have an inconsistency. If the other side is also 0, then that's okay. That just means that you don't have enough information to fix a particular solution, but the system is consistent. So you know when we have figured out when an inconsistency occurs. Look at the echelon form of your matrix. If you find, of the augmented matrix, if you find a row of this kind, all zeros followed by one single one, then the system is inconsistent. Ji. It means what? There's no answer, there's no solution.
Sir, अगर ये सबसे नीचे red में, if that wasn't 1, if that was 2, ये तब भी echelon form ही होता ना?
Even then it's inconsistent. अगर यहाँ पे 0 होता तो तब ठीक था. Well, yeah. The only point is
अगर यहाँ पे 2 होता तो then it's still an echelon form, right?
It's not echelon form because of that overkill I talked about. But you can make it echelon by dividing
variable,
2.
वो variable में भी होता है, not just coefficient. मतलब उसमें भी follow करना
हाँ,
होता है.
उसमें भी. So since we have decided that we will stick to echelon form, we will make the first non-zero number to be 1. We can make it. And if you then encounter a string of zeros followed by one single one, that means it's inconsistent. But your logic is correct. Even if we haven't reached there, even if we look at a 7 sitting over there, that means it's inconsistent. And a strictly triangular matrix which has ones on its diagonal is echelon. If you find that kind of echelon form, then that means you will have a unique solution. If above two cases do not hold, you don't have a strictly triangular matrix. You go a few steps before you fall down, then you will have infinite number of solutions, because then you will have free variables. So we have covered everything, and we know now exactly what happens, what kind of solutions are possible, and how can we tell, and how can we find actually all those solutions. Just reduce the matrix to echelon form. This is called the Gauss elimination method. And it always works. Either it gives you the solution or it tells you that there are no solutions. Why does it always work? How can I bring any matrix? So like this matrix. How can I bring it to any matrix to echelon form? Well, bringing this to echelon form is easy because the zeros are above non-zeros. I can just swap. That's an allowed operation. So maybe I should write, I had written it over above here. Any, I had written it somewhere. By using elementary operations, we can bring any matrix to the echelon form. Because if the zeros are above, I can just swap and bring them down. If I see some, if I had, for example, a non-zero number over here, if I see a non-zero number after a leading entry, I can just add that entry to the number below to make it 0. That's always possible because my leading entry is not non-zero, and I want to have something below it to be 0 to make it echelon. I can always do it, but just add it to the next row. And if my first number after the zeros is not 1, is some other constant, I can divide by its inverse to get a 1. So we have proved that you can always bring any matrix to echelon form. So this method always works. However, this may work, but this may be very, like, if we tried doing it for one 5 by 5 matrix. I hope we haven't lost Zoom. Can you guys hear me?
Yes.
Okay, good. So it's one thing that this always works, but it's another thing that how easily you can do it. Like we tried this 5 by 5 and kind of failed. A very interesting question to ask is, can we tell right in the beginning that if the solutions will exist or not? Because if the solutions do not exist, let's not waste our efforts in trying to find them. And if they exist, what kind of solutions they are? Are they unique or is there an infinite kind? That may be also important for your problem. So we will see later on other methods which can tell us about the characteristic of solutions without even solving the system. So this is just for later, but it's an interesting question to ask. Question आपका? Yeah, Gauss elimination is just what we have done. All I'm saying, you're given a matrix of coefficients, bring it to echelon form. And you can always do it. You will not fail with any matrix to do it. It's just going to take some finite step. Finite could be a million, but it will be done. And finally, you will get to know what are the solutions, or you will get to know that there are no solutions. once you hit the echelon form. Echelon form has the full information. Now this is just some more terminology useful to know because books talk about it. It's the reduced row echelon form. So what's the idea behind it? It's just that you can systemize, like we said that once we get this, for example, this triangular system, let me first explain it in terms of triangular system, then I'll go to more general echelon systems. Once you hit the triangular form, we know we have a solution that we can back substitute. Like this is the example from first class and this was our solution. But you can even systemize this process of back substitution. So instead of putting this z over there, what you can do is you can say, well, I'm going to eliminate z from this equation. I'm going to choose the equation 3 in this triangular system and eliminate z above it. That will leave only y. So that will be my solution for y. And similarly, I can take this z, eliminate z from the first equation, take this y, eliminate y from the first equation. That's going to give me the solution for x. And that's always going to happen because if this is solution, these are also systems of equations. Very simple one, but they are equations. So they are equivalent. Now, if this guy is matrix is of this form, (23)(6), then this guy is matrix is very simple. If it's a unique solution, if you had hit a triangular system, you can always reduce your matrix to this form. And then some constants over here. In this case, they are these. So like this part, the left-hand part is like identity in this case. You can always do it because you have the unique solution. So this process, if you keep continue instead of putting by hand, if you say I'm going to keep using row operations to get to my solution, if you do that, this is called Gauss-Jordan method. I don't know why people keep calling me. Well, Feynman once said that when he was a kid, he realized that there's no value in knowing the names of things. It doesn't tell you anything about thing. If you know the names of like 7 birds, you have never seen them, you don't know how they act, it's useless. So you encounter these names, but there's some logic behind it. You have to know that what's going on. So what's Gauss-Jordan is just one more computational step. But when you do that, suppose if I did not have a system like that, if I had a system which is echelon form or something like this. Damn, this Gauss guy, why did he wanted a 1? is this one. Now I know that x2 is going to be a free variable. And if I do the logic of Gauss-Jordan that I'm going to back substitute, I'm not going to be able to substitute anything into x2 because that's not present in the rest of the equations. It's a free variable. And you can see it over here. When I try to eliminate this guy for the x4 from the second equation, for my ease of back substitution, I will be able to eliminate this. I will be able to eliminate it from here as well. Similarly, I will be able to eliminate x3 by adding this guy up over here. But x2, all things below it are 0. No matter what I do, it won't be changed. So if I go to the Gauss-Jordan, if I apply Gauss-Jordan method, I will end up with a matrix like this. Very near to identity, but not really. And on this side, I will have some numbers. I don't know which one they are, so I'm just going to write A, B, C, D. But that's okay because we know that there has to be a free variable. So I just take that guy. When I construct my solution, I write it as 3x2 and I take it to the other side. And then I have an identity. And then I have a solution once I give values to x2. So that means when I complete Gauss-Jordan method, and I can always do this, I'll end up with something like that. Some matrix like this, or some matrix like this. So what are the properties of this matrix? They are in echelon form, but also they have the property that any column, any row, okay, so any non-zero number in a row, the first non-zero number in a row, the numbers in that column, all the numbers in that column are 0. Because you eliminated the numbers above, below it they were already eliminated because it was in echelon form. So the first non-zero number, which you know is going to be 1 because it's echelon form, all the numbers below it are 0 because it's the first one. Then you eliminate above as well. And you can do that. Once you do it, then you call this guy, both of these guys, as reduced echelon form. But I can't do it to the second number. That's okay. So the definition becomes that your matrix is in row echelon form. Then this is what you do. The first non-zero entry in each row is the only non-zero entry in its column. Above it and below it, you make everything 0 using this. But there is a possibility of this guy because below it there are no non-zero numbers which you can do. But then this is not the leading non-zero in this row. Well, I shouldn't say coefficient, anyone, coefficient or augmented. So you can do that, and this process is called the Gauss-Jordan elimination. So now, I don't know, I mean, I had thought I'll complete this chapter in probably 3 lectures. We have hardly done 2 sections. Huh? No, I just forget how much a sophomore knows. It's my fault, not yours. Should we stop here or? Okay, so let's stop here. And I I sent an email, I guess. So I plan to do online tutorials. So where we're gonna do some examples. I'm proposing Friday, something like 5 p.m. So someone told me that they will get back to me that what time is suitable. They didn't get back to me, so I'm just gonna propose Friday 5 p.m. हाँ? रात को 7 बजे हाँ?
They're going to be recorded as well, right?
Yeah. No, but the point is that they should be more free. They should be. You should be able to speak more, interact during those tutorials more than lectures. Huh? 6 is fine with me as well, but I have to know what other people think. Do they want to have their evenings free, or do they want to rest and then come back? Saturday is fine with me as well. So just think about it and somehow get back to me. So okay, now you're just one.
The thing is that regardless, Monday to Saturday, everyone has a different schedule. Some people come 6 times a week, some people come like a lot. So I mean, Sunday is one day everyone's free.
Sunday.
या आप रात को रख लें,
रात को कितनी रात को रखूं मैं? आधी रात को तो नहीं रख सकता.
हम लोग